Hello, F-sharp. Welcome back to our series of writing a fast dictionary in just F-sharp. Last time, where we left off is we finally got to the point where our custom dictionary appears to be faster than the .NET dictionary for the benchmarks that we are measuring. Now, one of the things I want to repeat often in the series is we're just using a subset of benchmarks that I would use if I was doing this for a real world scenario. I have pared them down to just these for educational purposes. These are the ones that I think kind of illustrate the ideas of what I'm wanting to get across to you in the most effective means possible. But I don't want you to think that, oh, this is all you would have to do to verify that this new dictionary implementation is better for our use cases. No, there would be far more. But with this subset, we're able to get a good determination of what the overall performance of our new dictionary would be for reading data. I'm not really covering removal of entries yet because my goal was to create the fastest read dictionary possible because I really care about a fast read-only dictionary. Later at the end of the series, we can go back with our fastest dictionary and then implement removal logic. So it would then be a general purpose dictionary. So what you're seeing now on the screen is the benchmarks from the last optimization that we did. And what we're seeing is that for integers, we are significantly faster than the .NET dictionary. And we're also a little faster for string keys. So that is fantastic. And real quickly, I want to review for you what that data layout looks like right now. So right now, what our layout looks like is we have an array, and we've kind of been referring to all the different entries in this array as like the different buckets, and a bucket has an entry, and each entry has a key and it has a value. Now, in our case, previously, the way it worked is you would have a key, you have some key, and that would map to some bucket. The entry into that backing array would be a reference to some linked list out on the heap somewhere. And so that is how we were dealing with collisions. When multiple keys were mapping to the same bucket, what we would do is we would go check the first entry into this linked list. And if it wasn't that one, we would go to the next entry and then to the next entry. And so we could have many keys mapping to that same bucket, and it just meant we'd have to search through this linked list. Now, what we did last time is we say, like, you know what? We would rather not have to go out. We would rather avoid this additional ref lookup if that key is that first entry. So we made this first entry a struct. And so it is actually, that data is in the array itself. The array is holding structs, which are the first entries into the linked list. So this has a key and a value in it. And it also has a reference to the rest of the linked list, which is somewhere else out on the heap. And so we are still using the idea of a linked list to deal with collisions if multiple keys are coming to the same bucket in our array. But that first one, that very first head, the head of the linked list is a struct, and its data is in the array. So if that first entry is the key that we want, we don't have to go somewhere else out in the heap, which is fantastic because if you have a good hashing function and you have a good function for spreading those keys out in the dictionary, in that backing array, you should actually have very few collisions. Typically you'll have one, maybe two keys mapping to the same bucket in that array. You're kind of running into the birthday problem at this point. And if you don't know what it is, go look it up. It has to deal with collisions. It's amazingly annoying. But often that first entry is the one you want. And so you don't have to go search in the heap. And this is how we got a lot of additional performance because we just had superior data locality. We removed a ref lookup to the heap, and we increased the probability that the data we wanted was already in the cache. So what we're going to do today is continuing that thought. It's like, okay, well, if a little bit of data embedded into the array is good, wouldn't like a lot be even better? And there actually is a technique for doing that called linear probing. That's hilarious because this is the second time I'm recording this, and that's the second time I made that mistake. Linear programming is a completely different thing that I actually do a lot of. Linear probing is what we're actually talking about. And with linear probing, the idea is that if you have multiple keys mapping to the same bucket, what you do is whoever gets there first gets that first entry, and then you just start scanning down the array looking for an opening, and you just insert it wherever there's an open spot. So what does that mean practically? Well, with linear probing, what you do is say, like, okay, well, I have my array. I have key 1, and it maps to this bucket. And so like, okay, well, I will put that in. So key 1 is here. Obviously, there's a value that goes with key 1, but right now I'm just really concerned with the keys. Key 2 comes in and maps to the same bucket, but there's already a key in here. And so what we will then do is move to the next entry and say, hey, is there something in here or not? If there isn't, we will insert this new key value pair into this next location. If this is full, saying like, nope, not available, we would then go check the next one. And we would just kind of keep iterating down the array until we found an opening. And our resize logic ensures that there will always be space in this dictionary for us to insert this key value pair into. Because once we reach a certain fullness percentage, in this case it's 75%, we resize the array and redistribute the entries to ensure there's always space for us to put something in. So we know if we keep iterating long enough, and even if we have to come back up to the beginning, there is going to be space somewhere in this array for us to put this new key value pair in. And the fact that you're just linearly searching through the array is where the term linear probing gets its name, because you're probing the array for an opening, and you are doing it in a linear fashion. There's also Fibonacci probing. There's quadratic probing. So there's different styles of this. The linear version is the most simple, and it's the one that we are going to use today. So let's look at what that code looks like so you can understand what this means practically. And so I'm going to go back into my fast dictionary test project. I'm going to go to linear probing, and I'm going to, let's look at a get struct value. We want to talk about adding an entry into here. And so I'm going to zoom in just a little bit, just to make it really easy for you to see. So this is my function for adding a key value pair where the key is a struct or struct-like. And if you're wondering, like, why do you have one for struct and why do you have one for refs? Because we have one down here for add ref entry. If you're curious as to that, go look at the video that has metaprogramming in the title, and it discusses like why we're doing that, and it's for performance reasons. So inside of here, we have this recursive loop function, and then we have some computation. So the first thing that we do when we have this key is like, first, we're going to compute the hash code. And in our case, we get the hash code. In our case, we want to make sure it's positive, and why that's the case will come up later. But we want to make sure it's positive, and so we're just using this bit mask to make sure that, hey, we're making sure that this is a positive integer. We then take that hash code and compute the bucket it corresponds to. So that key is always going to compute the same hash code, but as the dictionary changes in size, the bucket index that it actually ends up going to can change. And then we call this loop function, which is this logic up here. And it's a recursive function. And so this is one of those things that is very fsharpy, very functional programming. If we were writing this in C# and some other imperative language, we would probably be using a while loop. In F#, we use recursive functions that call themselves. And you might think like, oh my goodness, this is going to be a performance penalty. It is not. The F# compiler is smart enough to look at this and turn this into a while loop when it becomes IL. So don't be concerned that this is going to cause a performance penalty for you. It's not. Often the F# compiler is smart enough to turn this into while loops for us. Okay, so we have a hash code and we have a bucket index, and that bucket index is where we're going to start our search. We check, hey, is this bucket index within the bounds of the array? And why that's important will come up in a bit. We get the first bucket, that first entry by ref, because we don't want to actually have to copy all the data over. We're just like, hey, just give it to me by ref. We check, is it available? Is there something in here already? If it's not, if it is available, like there's nothing in it right now, and we're trying to insert this new key value pair, go ahead and write our data in there and say like, yep, increment the count. Like we have added a value to this dictionary. If it's not available, we will then check, hey, do the keys match? Because if the keys match, we're basically just overriding the value in this case, which is what we want to do. And notice there's no incrementing of the count here because we actually haven't added a new, the number of entries in the dictionary hasn't changed in this case. If it's not matching, we still need to find a space to insert this key. And so what we're going to do is we're going to call loop again, except now hash code is the same, but the bucket index has increased by 1. Come back up. Okay, are we still within the bounds of the array? And now you might see like, hey, why is that important? Because as we are linearly probing through the array, we're just going to keep incrementing and search. Eventually, we might go off the end of the array, and so it needs to loop back to 0, which is why there's this else case. So if we keep searching, we get to the end of the array, like, hey, we haven't found anything, we're going to hit this else branch. It's going to say, okay, well, you need to keep searching. I know there is room in this array because I always resize it before I run out of space. I just need you to start over at the beginning of it. And again, this is the idea of that linear search, that linear probing through the array to find space available. It will find it at some point, and it will write it in. Okay. Then let's look at getting a value out. And it's going to look very, very, very similar. We're going to do the same thing. We're going to compute that hash code. We're going to compute what bucket index is it's supposed to go to. And then we are going to, hash code. I was moving some stuff around in between edits. So yeah, this should be get struct value. I got to edit this out. Okay, we're back. Got it fixed. So what's going on? Compute that hash code, compute the bucket index, start the search with this loop. And what we do is we say, okay, we're going to recursively call this loop with the hash code and the bucket index and say like, okay, is that bucket index within the bounds of the array? If it is, we're going to check our entry and say like, hey, do the hash codes match? And are the keys equivalent? If so, return that value. If not, they don't match, we need to check, is it occupied or not? And this is where that bit mask is coming in, where we say like, hey, we want to make sure that our hash codes that we are using in our dictionary are positive. And the reason is because our definition for is occupied is if is available, hey, is it less than 0 or not? Because we're using the topmost bit of the int to indicate whether it is actually, if there's actually an entry in here or not. And so we've kind of reserved that bit for our purposes. So negative numbers have special meanings in this dictionary. So that's why we had to make sure our hash code was positive, because that top bit indicates is it occupied or not in the kind of emptiness it has. Because we won't get into tombstones. Well, actually, we are going to get into tombstones right now. So we're going to say, hey, is it occupied or not? And if it is, then we need to continue our search because we checked it. It wasn't that one. And we're just going to keep searching down. What happens if it's not occupied? Well, it's entirely possible for us to not for us to have like a hole. So let's say that this here, get my styles here, like this here is a hole, right? There's nothing here. And so we are trying to do a lookup for like, let's say K3, and this happened to map to that same bucket. We'd say, is it here? No, K3 does not match K1, go to the next one. Hey, and let's say that K2 ended up in here. We would then come down like, hey, K2 does not match K3, keep searching. And then we got to this empty spot. And we know because of our insertion logic being this kind of linear, just like check, 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 check. If K3 was in here, it would have taken up this spot if it had been inserted, because it would have just been linearly going through and it would have taken up here. We know it's not going to be past this point. So if we come to this emptiness, we know K3 is not in the dictionary, and therefore we need to return a key not found exception. That gets a little bit more complex when we actually have to have removals. We use a thing called a tombstone to indicate like, hey, the thing is not here, like there's not a key here, but it used to have a key here, so you should still count it. You should still keep searching past me. Those are kind of nuances that we're not going to really cover yet. Like I said, at the end of the series, we will talk about implementing removal logic and all those nuances. But this is that search. And so if we come to an empty spot, we know that the key does not exist in the dictionary, and therefore we can return that key not found exception. Okay, else we're going to, if like we go down to the end of the dictionary, the very end of that array, we'll do that loop and start searching from the beginning of the array. So you'll see like this logic has a lot of symmetry with the insertion logic. It's essentially the same thing, except it's like, hey, I'm looking for a key versus I'm looking for a place to put a key value pair. So you would think that with the superior data locality that we would get potentially better performance with this. No, we do not. And in fact, we are quite sad. So we went from 40 microseconds for the integer keys and 10 key counts to 61. Now for 100, we're at 45. So that's still pretty good. But then when we go to 1,000, previously we were at 66 microseconds. Now we're at 70. That's pretty close. At 10,000 integer keys, we're at 90 microseconds. Here we're 97. It's still kind of like pretty close. And so like this is clearly, as we're going back and forth, like this is clearly not a win. This is not a huge win. And in fact, for strings, it's like this is worse. So 366 microseconds versus 237 previously, 318 microseconds previously for 10,000 strings in the dictionary to 520 microseconds. Geez. And there's this like weird mystery allocation that the runtime thinks it needs to do for some reason. Like, so that might be throwing it off, but like clearly this was not just a solid win. Now for the engineering question. Why? Why is this not a win? Why is this not a clear win? Because everything we know about, data and caches, like cache is king when it comes to performance. Like you need to make your algorithms predictable. You need to make sure your data is in cache. This, by its definition, means that you have a very high probability of having cache misses. You would think that this would be better because everything's together. Why? Why is this going on? There are two main culprits. One, let's talk about the first one. When you have a miss with our embedded head, so like this embedded linked list, when you have a miss, and what I mean by that is like you come to this bucket, it's not the first entry, you now need to go down this linked list. The advantage of this strategy is that you know that everything in this linked list mapped to that bucket. So all of these have a legitimate chance of matching. With this strategy, though, it is entirely possible And let me change this up a little bit. It is entirely possible, and you're like, you know what? I need the eraser. It's entirely possible we are in this situation where, put these lines back. Hey, we put K1 in here, but then, K7 went here and it mapped to here. And then K9 mapped to this bucket. And so K2 ended up being all the way down here. K7 and K9 are in their home buckets, which means like they got inserted into the bucket that their hashing function put them in. K2 and K3 want to be in the same spot as K1, but because they are getting inserted after K7 and K9, like this K2 ends up being a long way away from K1. And so not only so this could get really bad, like really, really bad as your dictionary gets more and more densely packed. And so this could end up being really far away, there's two really bad things about that. You have to compare against K7, which never really had a legitimate chance of being a match. But you didn't know that because your strategy for dealing with collisions was like just look for an open spot. So you have to check if you're inserting K2, you have to check K7, you have to check K9, and then you're finding an empty spot. Like so, so you're going to do more key equality checks than you would with this strategy, because even though this might be spread out, you know that all the keys in this linked list did map to that bucket. The other problem has to do with the fact that, hey, yeah, it's the fact that this thing could end up being really far away. So you're going to do more. The first problem is you're going to do more key equality checks with keys that actually had no legitimate chance of matching. And you're potentially going to go really far away. So even though the whole, you would think that whole array would be in cache, it might be far enough away that's not on the same cache line anyway. And you might even end up having to go all the way back up here and starting to search down here. So by being lackadaisical in how you insert these, but which is kind of what I'm referring to with the linear probing, the linear probing strategy, it is a very naive strategy for inserting key value pairs into your dictionary. And so it's relatively easy to come up with some really poor cases for it. So you would think that you would get some advantage from it, but you really don't. Like these other factors become a really significant issue and mitigates the performance that we potentially could have gotten. So going forward in the series, we are going to use some more sophisticated strategies for dealing with this, because this idea of getting all the data into a single array, that's a good idea. It is a good idea, but we need to be smarter about how we manage it so that we don't get these really degenerate cases that, really kind of destroy our performance. So I know this wasn't exciting, yes, we got better performance this time. We didn't, but this is real engineering. I'm wanting to take you through the process so you develop that instinct yourself. And there's gonna be a lot of times where we try things and just completely blew up, didn't work at all. But it doesn't mean the idea was bad. It means that we have to work on the implementation is how I would put it. So we're going to keep going in this direction, and there's some really fantastic optimizations we're going to be able to do on top of this. So thank you so much for spending some time with me. I really appreciate it. Something that'd be really helpful for me is if, what other strategies do you think would be fun to try out in this situation? I'd be really curious. I have the ones that I tried out, but what would be really fun is if people suggested some ideas, and then at the end of this, we kind of have an outtakes or some bonus stuff from ideas from the audience about hey, what about this strategy? What about this strategy? And it'd be fun to get that now before you see the other things that I'm going to end up doing. And so, yeah, I'd be really curious, what are your ideas for how to improve this insertion logic? Well, until next time, thank you for spending some time with me. I really appreciate it, and I hope you have a wonderful day. Bye-bye.